Hey everyone, thanks for joining. This is sort of the, I guess, first reiteration of the RL and Agents reading group. Today, we're very excited to have Mattie Fellows joining us. Mattie is currently a postdoc at the Flare Lab in Oxford, who is interested in a broad spectrum of RL, especially methods that combine powerful theoretical insights with practical empirical benefits. The paper that will be presented today is Simplifying Deep Temporal Difference Learning. I really enjoyed the paper because it does a lot of things right. It takes DQN and tries to improve the stability while also simplifying. I think it's very nice seeing methods trying to simplify work. I feel like there's a trend to make things more complicated, and also increasing sort of the speed of DQN using the PQN algorithm and reducing the memory requirements. I think that's basically it. So I'm going to hand over to Mattie.
Cool. Yeah, thank you for that. Thanks for the introduction. Yeah, I've got like a presentation basically. So let me just share my screen. Cool. As I was sort of saying earlier, yeah, there's quite, there's a few bits to get through, but if you've got sort of like, if you've got kind of like clarifying questions to ask during the presentation, like please feel free to interrupt me and I'll be happy to answer. And then if there's anything kind of, people want like a bit more of a deeper or longer discussion about, maybe we can save that till the end, or if you don't, want to sort of discuss things whilst being recorded, then we can save that till the end, and I'm happy to stick around a bit longer afterwards if anyone wants. Can everyone see the screen okay? Is that all right?
Yep, looks good.
Amazing. Yeah, cool. So I'm going to be presenting a paper that we presented at iClear this year, is Simplifying Deep Temporal Difference Learning. This was done in collaboration with Matteo Gallici. He's at University Politècnica de Catalunya in Barcelona, and it was a kind of Flare collaboration. He was visiting our lab for an internship, so we decided to kind of work on this. I did more of the kind of theoretical side, so probably the talk's going to skew a little bit more that way, but I've got a few slides as well on like the implementation. Cool. So yeah, part one. I thought I'd talk about maybe just understanding temporal difference, because I feel like it's, it's the sort of bread and butter of reinforcement learning, but it's something that I feel like there's kind of a bit of a lack of understanding of what it is and how it works. So the first question I kind of want to be able to answer is like, why is TD just as an algorithm so inherently unstable? If it's unstable, then how can we analyze TD? And then using this analysis, is it possible to develop a way to stabilize TD to kind of get provable convergence results? So in answer to the first one, basically the reason why it's so unstable is because it's not actually gradient of everything. Some people sort of assume because you use things like Adam and various stochastic gradient descent methods to do the updates, it's a gradient. It's actually not a gradient of anything. It comes under a more broad class of algorithms called stochastic approximation. So how can we analyze this? Well, whereas traditionally, if we have like a gradient, we can look at things like the Hessian of the objective, but for TD, we actually use the Jacobian instead. And then sort of what we showed in our paper was one way in which we can stabilize this is by introducing a combination of LayerNorm regularisation and a little bit of L2 regularisation. But we really hope that this research kind of leads to other people thinking of other ways also that could stabilize TD that might be more applicable in other settings. Cool. So just to mention some like related work, our paper basically builds on these three papers. This really beautiful paper that's actually inspired quite a lot of my research when I read it ages ago by Klitzis and Van Roy, like an analysis of temporal difference learning with function approximation. It's a really nice kind of asymptotic analysis of linear TD, and it also includes a very famous kind of nonlinear counterexample to show like divergence of TD in a nonlinear setting. There's also this brilliant paper by Bandari which looks at essentially a non-asymptotic analysis of linear TD. So it sort of analyzes how quickly TD kind of converges. Some of the techniques used in there were like a kind of starting point for the next paper, and that was a sort of paper here, the third one, why target networks stabilize temporal difference methods. Me and my collaborator Matt Smith kind of wrote this looking at why target networks can sort of induce stability in TD, and we also introduced the technique that we use in this paper to be able to extend all this analysis to the kind of nonlinear, non-finite Markov process setting. Cool. So what is the goal of TD? Well, obviously we want to be able to solve a Bellman equation, typically using some kind of function approximator. So here's a Q function approximator, and what we want to do is we want to solve this Bellman equation. So we introduce a parametric function approximator, typically a neural network for most deep reinforcement learning applications. And then the Bellman operator for a particular policy essentially propagates this kind of function approximator one step through the dynamics of the MDP. So you sample from the state transition, you sample from the policy, and you get the kind of propagation of that Q function one step through the dynamics of the MDP. So solving an optimal Bellman equation is also sufficient for solving the RL problem. So we can write down the optimal Bellman equation, which is kind of greedy with respect to the next action. And for most RL problems, when we're concerned with learning an optimal policy, we want to find like a parameterization such that this Bellman equation holds. So there are sort of two methods that were initially developed for this when it was kind of when these kind of algorithms were designed. And the first one is to kind of look at like the mean squared Bellman error. So it's like the difference between the Bellman operator acting on the Q function, with respect to some kind of sampling distribution over the state action space. So it should have kind of coverage over all of the state actions that you need to visit. And the idea is to kind of like, by minimizing this norm as much as possible, we can learn a parameterization that should approximately solve the Bellman equation. So direct methods just go ahead and minimize this using stochastic gradient descent. So if we go ahead and do this, we see there are, we get a kind of gradient that's like proportional to these terms here. So I've just sort of passed the gradient inside the mean squared Bellman error, and we get this kind of gradient term. However, this kind of like raises a problem. So if we consider expanding the kind of Bellman operator term here, so the gradient through the Bellman operator term, we get this kind of, and multiplying it by the Bellman operator when we expand the brackets, we get these kind of two expectations here. There's the first one is equal to the expectation of the reward plus the Q function one step into the future, and the second one is an expectation with respect to the gradient of the Q function approximator. And this is kind of problematic because to get an unbiased gradient estimate, essentially what we need is two samples from the transition distribution, as we see here. So we need a first sample for the first term and then a second sample for the second term if they're going to be unbiased. So that's the first term there, that's the first sample, that's the second term there, that's the second sample. Unfortunately, for most learning problems of interest, this isn't actually physically possible. You know, it's very difficult to be able to return to a particular state and be able to kind of resample from the state transition distribution. And even if you could, it would be hugely wasteful to have to plan to be able to do that. So if you think about this, we'd have to return to the same state. We'd have to take the same action, and we'd have to see what the kind of next state would be for this. So for this reason, it's known as the double sampling problem. It was sort of a key issue with using direct methods. One way that people kind of tried to get around this, either directly or indirectly, was just to simply drop the offending gradient term. If we just drop that term, we can kind of get rid of that, and we can kind of arrive at the TD update, which kind of removes that problematic term. And this had kind of some, it had apparently some kind of like, I guess, direction from like a neuroscience type understanding. As far as I'm aware, there's some people argue that kind of temporal difference is kind of used to kind of update like neuron systems of neurons. I'm not sure how true or not that is, but for RL, it seemed to get around this issue. So what happens is we sample from a distribution where it's over state action pairs, and that can be different from the actual target policy that we're trying to do the policy evaluation on. So that mu can be different from pi, and then we observe a single sample from the transition distribution and then sample from the target policy, and that gives us a way to update our parameters. So looking at this, we can see that direct methods are obviously they're a gradient on the mean squared Bellman error on average. So on average, if we have like a loss landscape, updates will always kind of go downhill, and mathematically it's kind of well understood that this can yield convergence. This standard kind of Robbins-Monroe analysis shows that in the stochastic case, for most regular systems, we should converge at least to a local minima. Because TD methods aren't the gradient of any function anymore, we've now got no kind of guarantee that these updates will even be kind of on average going downhill. So this is essentially where the cause of instability in TD comes from. So we've got no general convergence guarantees, and there actually exist counterexample MDPs that we'll kind of discuss a bit later, where you can have provably divergent results in TD. Cool. So in the tabular setting, this is kind of the easiest kind of setting to analyze, where your Q function approximator is basically just a lookup table. For the tabular setting, if we just do our analysis in that space, we can actually show that TD is provably convergent. However, like, as I said earlier, tabular settings quickly grow intractably large. It's not possible to kind of have a lookup table for every state action pair, and you can't kind of include continuous domains. So in reality, what we want is some kind of function approximator like a neural net. And this to me is kind of like, a good word of warning. I see a lot of papers when I review that do analysis in a tabular setting, and they claim all of these wonderful results, but actually in reality, something that's seemingly convergent in a tabular setting can lead to issues because of this kind of issue with the gradient when we use kind of function approximators like we do in deep reinforcement learning. So there are two kind of cases that can cause this this instability. The first is if the sampling distribution is not the same as the stationary distribution. So if the sampling distribution is the same, then and we're sampling from the stationary distribution under the target policy, then that sampling regime is known as on policy. Obviously, initially, the sampling distribution won't be the same as like the ergodic kind of stationary distribution that the system converges to, but given enough time, that will converge, and therefore we will recover stability in a limit. More generally, however, sampling is off policy. We have some other policy, be that an exploration policy or some historic policies that we used kind of previously, like in Actor-Critic, and all data is kind of going to be sampled from those different policies when we do this kind of updating. So under that regime, we have off-policy sampling. So convergence depends on both whether this Q function is linear and also the type of sampling regime. So as I said earlier, Tiklitis also came up with this example to show that on-policy sampling with nonlinear function approximator can also lead to provably divergent TD algorithms. And we can kind of summarize these results here in this table. So if we have an on-policy sampling regime and our function approximation is linear, then we can get convergence. For all other cases, so if we're off policy or if we're nonlinear, then we have kind of like counterexamples showing that TD can be divergent, and we're going to look into that a bit later in the talk when we try and characterize the stability using the Jacobian. We actually see that these two cases come out quite naturally from that. So in most kind of like settings in deep reinforcement learning, we're typically in the off policy case, and we're almost certainly going to be in the nonlinear case using something like a neural net as a function approximator. So it's really important that if we're to use these algorithms that we have kind of convergence results. So the key takeaway is that tabular analysis is often not sufficient to understand deep RL. Okay, so how can we analyze TD? So going back to that second question that I wanted to ask. So as TD is not gradient descent, it kind of falls into a broader category of algorithms called stochastic approximation. So key to analyzing TD is examining essentially the stability of the expected update. And this was kind of one of the contributions that Bandari made, was saying, okay, we need to look at what they call like path mean kind of expected TD update, and then that'll give us kind of essentially the criteria with some additional kind of assumptions about the variance of the sampling to prove convergence of the overall kind of TD algorithm. So I can define the expected TD error vector as this thing here. So it's just my TD update R plus gamma Q, one step into the future, minus Q times the gradient of Q with the expectation taken with respect to the kind of the stationary distribution under the policy. And we can see that like the expected TD update is given by this this update here. And the idea is you know, intuitively we can kind of see that as the TD update kind of tracks the expected TD update as your kind of step size slowly tends towards 0. And you can kind of like see this from like a kind of pictorial thing. So if we have a large alpha, our step sizes are going to be quite large. They're going to kind of, because of the variance, they're going to kind of diverge slightly away from the expected update. But as we kind of shrink our alpha down, these kind of these updates get closer and closer to the expected update. And actually, there's some really nice analysis that's done for stochastic approximation algorithms that show that in the limit of alpha tending to 0, you actually recover a system of differential equations that the kind of the algorithm sort of tracks, and that's sort of like a limiting system of ordinary differential equations that can be used to prove stability. But for our analysis, we can kind of get everything we need to know just by sort of looking at the expected TD error vector. So if TD converges, then it obviously must converge to a TD fixed point, and if one of those fixed points exists, it's a fixed point such that this kind of expected update equals 0. So intuitively, that basically means every time, on average, I update my parameters, they're not going to change anywhere; they're just going to remain the same. So the solution to that equation is known as the set of TD fixed points. So how do we characterize convergence using this? Well, an intuitive approach to characterize convergence is to be able to prove contraction of the expected updates. So if like the distance between that fixed point and the parameters on average is always decreasing with each updates, then the updates should converge in the limit. So you can kind of think about this sort of geometrically like this. If I have, you know, like a starting point phi naught here, if I keep updating my parameters, and on average they're kind of getting closer and closer to the fixed point phi star, then eventually convergent, you know, they should sort of be able to prove that they converge to that fixed point in the limit. So a nice way to kind of measure this, and sort of way that we measure this in our paper, is using the 2 norm here. So we find the distance between each parameter on average and the fixed point. So what does this mean? Well, formally, what we want to show is that the update is a contraction mapping. So the update one time step into the future is less than equal to the distance between the fixed point and the current parameter for some alpha. Obviously, we have like typically a decreasing step size alpha, so it doesn't need to hold for all alpha. As long as there exists some alpha that's greater than 0, eventually we'll kind of pass that threshold, and our updates will be convergent for all future alpha as alpha tends to 0. So I hope that kind of makes sense. That's kind of how I like to sort of think about this thing geometrically. So how can we look at this? Well, the Jacobian we actually see as an incredibly powerful tool that gives us essentially the kind of ingredients that we need to be able to show convergence. So I'm kind of just going to walk through this quickly to show how we can kind of write this update using the Jacobian. So recall that we wanted to show this property. So the point one step into the future has to be strictly closer to the TD fixed point than the current point on average. And to be able to analyze this, because we're dealing with nonlinear function approximators, if we had a linear function approximator, this we could just write this kind of thing in a matrix equation, and it's kind of easy. But for nonlinear function approximators, we need to kind of do a little trick to be able to kind of show this property holds. And this trick, what we do is we kind of we consider the line joining a parameter in parameter space to the TD fixed point. So here's my line here in this kind of like pink potato thing, joining the kind of point to the TD fixed point. And what I can do is I can write the Jacobian as the kind of the derivative with respect to this vector, and then I get the kind of Jacobian matrix. And then essentially using the fundamental theorem of calculus, so the kind of regularity assumptions that apply for that, essentially to continuity basically, we can write this update in this form. So what we have the kind of the parameter 1 time step into the future can be written in terms of the parameter, now phi star minus phi multiplied by this kind of like big matrix here on the left, I plus alpha of the Jacobian. And we call this thing, I call it the kind of path mean Jacobian. So we can kind of think about it as like the average of all Jacobians kind of joining our parameter phi to the TD fixed point phi star. If we were in a kind of gradient descent setting, this would be the Hessian, and you could kind of think about this thing as like the average curvature basically from your point phi to phi star, because this thing isn't actually a gradient anymore. It's not sort of technically the curvature, but essentially it acts in exactly the same way as what a Hessian would for stochastic gradient descent. Cool. So substituting in, we can see that we can always upper bound this thing by the norm of the matrix. So I plus this kind of average Jacobian multiplied by the kind of norm of the parameter at time step now and the TD fixed point. So we see that if we need to recover this kind of this contraction mapping property, written at the top here, we want to show that this thing on the left has to be less than equal to phi star minus phi, then a sufficient condition for stability is to be able to show that this matrix norm is always less than 1. And then if we've got that, we've got this kind of contraction property, and then a lot of the rest of the maths is just kind of cranking the handle on kind of dealing with the stochasticity. But being able to show this is kind of, if we can do that, we're kind of, we're most of the way there to showing stability of TD. So we see that this property holds if this kind of Jacobian, if its kind of spectrum is always kind of negative for all unit vectors almost everywhere. This kind of leads one problem is this is great because it's formalized kind of stability in terms of this like simple matrix, but in practice we don't actually know where the TD fixed point is. Obviously, if we did, we'd just go straight there, and even if we did, we'd have to be able to kind of like calculate this line integral between our point and the TD fixed point for every possible point in the system. So while it's kind of mathematically a nice object to be able to check, we kind of want to be able to get a kind of object that we can check for real algorithms in practice. So we can introduce just a stricter but simpler condition, and that's simply just to verify that the Jacobian itself is negative definite for all test vectors x almost everywhere. And this is a much simpler condition to verify, and it's the condition that we use when we're deriving our kind of results on stabilizing TD. So in our paper we kind of highlight this Jacobian as the kind of TD stability Jacobian, and we sort of try and introduce the fact that the stability of TD really is just guaranteed by this object, and developing kind of algorithms and methods to be able to ensure the negative definiteness of the TD Jacobian really is key to unlocking kind of stable algorithms. Cool. So yeah, I've put this in a big box down here just to reiterate that Jacobian having strictly negative eigenvalues almost everywhere is key to be able to kind of show stability for this system. Okay, so
a quick question.
Yes,
we have a question in the chat. Sorry to interrupt. So there's a question asking: are you considering only convex formulations or non-convex and non-concave ones?
Yeah, that's a good question. Yeah, so it's basically, yeah, it's like convexities. Yeah, if you're in a Hessian regime, obviously, yeah, it's essentially the equivalent of a convex system. But what we're kind of showing is that what we want to show is that there exists a kind of, like limit where you recover a convex system. So essentially for the LayerNorm that we introduce later, there'll be a certain K that recovers like a convex system. But on the way to that's kind of provably stable, but on the way to doing that, you'll have non-convex systems that are also stable just by kind of moving into that regime essentially. Yeah, good question.
Cool.
Yeah. Cool. Yeah. So looking at this, looking at this Jacobian actually allows us to identify the causes of instability. So when can the Jacobian have positive eigenvalues? So if we go back to this thing, we can kind of plonk in the kind of the Q function into the definition of the Jacobian, and we get this this form here. So we have like the first term, which depends only on the first order derivatives of the Q function approximator, and then this second term that depends on the second order derivatives of the Q function approximator. So if we consider just this first term, so to show that the first term has negative eigenvalues, we essentially need to be able to show that this relationship here holds. If we consider like a linear setting, the term that's just disappeared in gray will tend to, it doesn't exist, it's zero because the second order derivative is zero. So in the linear setting, we'd need to be able to show that this kind of this inequality holds. So interestingly, this only holds if the expectation kind of one time step into the future in the Markov chain is equal to the expectation at the current time step. So that only holds again in that kind of limit of tending towards the stationary distribution for on-policy sampling. If that's not the case, you can kind of cook up a counterexample, which is essentially what Baird's counterexample does, to show that actually this kind of inequality sign is flipped, and therefore you get kind of provable divergence because you're kind of expanding on every time step. So this kind of covers this kind of key properties. I said that people had found that from Baird's counterexample, essentially that TD can only be proved to be stable in the linear case if sampling is on policy or essentially close to on policy. It can tolerate a bit of off policiness, and in our paper we actually derive essentially a condition that measures that. But in general, for off policy sampling, you can't, if you just that there exists like sampling regimes that lead to provably divergent TD for this reason. So yeah, as I said, famous paper by Baird in 1995 came out to show that there exist counterexample MDPs where sampling is off policy. So the key takeaway is that off policy sampling is a source of instability in TD. If we return to this second term here, we may have, for example, like on policy sampling. So the first bit of the Jacobian is not contributing anything, anything to the negative. It's the first part of the Jacobian is negative definite. We then need to show that this kind of second part is also negative definite. So the second term is zero for like linear function approximators, but for nonlinear function approximators, it's non-zero. And it's in general, it's not possible to be able to show that this property holds, that this isn't like that the kind of eigenvalues of this matrix aren't less than zero. And this is essentially how Klitzes came up with their, and Van Roy came up with their counterexample. They generated an MDP essentially to show that this term is always positive, and that always leads you further and further away on average from the TD fixed point. As I mentioned in the intro, this led to kind of provably divergent counterexample MDPs for nonlinear function approximators even with on-policy sampling. So again, the second key takeaway here is that nonlinear function approximation is a key source of instability in TD. Okay, great. So we've got all of these properties of TD. For a while, they kind of seemed like a bit of a fatal blow for developing kind of practical TD methods using nonlinear function approximation or off-policy sampling that would be stable. But if we look kind of carefully at kind of essentially, shifting these eigenvalues to ensure that the TD Jacobian is always negative definite, at least in a limit, then this allows us to kind of provably stabilise these TD updates. So to do this in our paper, we kind of look at this. We look at this kind of simple neural network Q function. So I'll just put a little diagram of it up here. We have our state action kind of input on the left. We have a linear layer multiplied by big matrix M. The outputs of those linear layers are then sent into a kind of Lipschitz pre-activation, smooth Lipschitz pre-activation. That then goes into a LayerNorm layer, and then we can have like a post activation that's also Lipschitz. That then gets transformed into a final kind of linear layer with this vector W, and there's our kind of Q function approximator. Yeah, we look at this kind of simple, like sort of fairly shallow network because essentially if we can prove stability for this, it kind of doesn't really matter what comes before this, as long as this is at the final layer of your Q function approximator, then the results sort of should hold. Okay, so under mild regularity assumptions, our first kind of result is to tackle the kind of nonlinear TD term. So under mild regularity assumptions using the k-width LayerNorm Q function, we can kind of show that this term here actually tends to 0 with increasing k at the rate of square root of 1 over square root of k. And this essentially is very similar to the kind of theorems you get in like the neural tangent kernel papers. I don't know if people are familiar with that, but essentially they kind of show that like the Hessian diminishes at the same rate root 1 over k, and therefore in the limit of a really wide neural network you kind of recover essentially a Gaussian process using like a linear tangent kernel, which is kind of the gradient of the network. So for the linear term, this kind of is very similar to existing results in neural tangent kernel theorems. So the key takeaway is that as k becomes larger, eventually the LayerNorm will start to mitigate nonlinear instability. Okay, the off-policy term is slightly more tricky. So if we kind of go ahead and sort of do this analysis using that Q function approximator, we arrive at this expression here. So again, we have this kind of we split our test vector up as a vector associated with the matrix weights xm and the final layer weights xw. And we kind of see that the matrix layer weights, they kind of eventually, their contribution to this will eventually shrink with increasing k. However, we do have this kind of like residual term that characterizes the stability of the final layer weights. And the reason kind of essentially for why we can then target this is because of our LayerNorm. LayerNorm basically re-normalizes the inputs of the kind of operator such that this kind of like norm property holds. And the nice thing about this is that it doesn't depend on the sampling distribution. So regardless of the sampling distribution, this kind of LayerNorm property will be able to hold, which is why this term doesn't depend on the sampling distribution. And essentially what we're going to be able to show is that we can tackle this term just by introducing a small amount of L2 regularization and only over the final weights. And the nice thing about it is we know the kind of amount of L2 regularization that's needed. Essentially, it's proportional to gamma L post over 2. So L post is the Lipschitz constants for that final activation. For most activations, it's typically 1. Cool. So let's put this into practice. So yeah, we kind of have almost surely this property here from our kind of 2 results. So we can mitigate this term by introducing a small amount of L2 regularization. So as I said, if we do that, we then kind of can get rid of that kind of sort of first term, and then like if for any eta greater than 0, that will kind of push this thing towards being negative, and then for the rest of the weights, we can just put a tiny little bit of L2 regularization on, just to kind of ensure that formally all the kind of eigenvalues of this matrix are going to be pushed towards being negative. So essentially all we need to do is we need to use our LayerNorm Q function approximator, and then use this kind of regularized TD update here, which I've written. So we have this term gamma L post over 2 squared times eta, which targets just the kind of final layer weights, and then this little tiny sort of bit of L2 regularization that targets the rest of the weights in the matrix, and then that will recover that inequality that we've got at the top there when we find the Jacobian of that update. The nice thing about this is that obviously under these regularity assumptions, using this LayerNorm Q function, so for any eta greater than 1, there exists some finite k such that the TG Jacobian has negative eigenvalues almost surely. And sort of going back to the question we had earlier, this is exactly analogous to kind of recovering like a kind of convex optimization for some finite k. For most settings, we don't obviously need to take k that large. There'll exist some kind of regime, whether that's provably convergent or not, but there'll exist some convergent sort of regime in between where the updates will just converge to a local minima instead. So that kind of is a nice way of connecting the theory to kind of what's going on in practice. So the key takeaway is that LayerNorm plus L2 with a suitable network width can stabilize TD. The question then is, well, we've put this LayerNorm in, we've done all this analysis, why not just add a massive L2 regularization term instead of the LayerNorm? And the issue with that is that just adding L2 regularization on its own, in principle, it can stabilize TD, but you'd need a really large eta. And as eta gets larger and larger and larger, this essentially just recovers a quadratic optimization problem with a minimum at 0. So this just pulls the TD fixed point towards a trivial solution at 0. So in practice, we kind of want to avoid adding L2 regularization as much as possible. So with this, we kind of came up with a recommended recipe. So the first one is just to try it using LayerNorm in the Q function approximator. If this is then unstable, you can increase the layer width until stable up to a tractable limit. And then if still unstable, then you can add a small amount of L2 regularization to the final layer weights. We found empirically that this works in pretty much all environments that we tested in. The only exception was like Baird's counterexample, which is like a counterexample MDP. So we can see that really L2 regularization is only, empirically seems to be needed for like particularly nasty MDPs that have almost been designed to prove divergence. So yeah, Matteo did some experiments on this just to kind of see this in action. So we see that the kind of like yellowy goldy curve here is just the standard result from Baird's counterexample, and you can see the kind of parameters diverging as the loss increases over episodes. If we just introduce a little bit of L2 regularization, it kind of does a little bit to stabilize this thing, but it doesn't, it doesn't do much. You need a lot of L2 regularization to be able to stabilize it. If we introduce LayerNorm, it actually goes most of the way towards stabilizing this. And as I said, like for most empirical problems that we looked at, LayerNorm alone was sufficient. You can see even with this particularly nasty counterexample, LayerNorm alone is kind of nearly stabilizing it. And then once we add the kind of L2 regularization, we then get kind of stable updates. Yeah, so this was a nice kind of encouraging result. So the key results from our theory that allow us to develop provably stable DFRL algorithms. This means that we can get rid of the replay buffer. We don't need to use DQN anymore, and we can get rid of the target networks. So by doing this, we kind of get rid of a lot of the overhead and implementation problems that have been associated with DFRL. I also would love to see, I think there was one paper from, I think McGill recently that looked at other ways to kind of show that Jacobian is negative definite by using ResNets. I'd love to see like a whole zoo of, other approaches. Like LayerNorm, is definitely not the only way to do this. It'd be really cool to see researchers kind of try and develop other methods to do this. So in the next section, I'm going to talk about PQN, and we will basically use this insight to develop a state-of-the-art algorithm that offers a significant speed up and simplification of kind of state-of-the-art Q learning algorithms. Cool. So just
quick question before we get there. So someone asked, I guess they also answered it, but I was also curious. I guess what class of activations do you consider? Is it all Lipschitz continuous?
yeah.
So
yeah, exactly. Yeah. So basically, the pre-activation that can be any smooth activation. So yeah, anything apart from ReLU, and if you have a post-activation, that has to be an activation that's also smooth and passes through 0, which is like most activations, smooth activations of interest. Yeah.
cool.
Yeah, good question. Yeah.
Another follow-up question.
Yeah.
I'm not sure if you've already spoken about this, but they ask, do you think the idea inductively extends to n-step returns? I'm not sure which idea.
I mean, I'll actually talk. So later in the paper, we actually developed PQN using lambda returns, basically. And empirically, it seems to be fine. I haven't done the analysis to formally confirm it, but yeah, just as a kind of like, like from my mind now, I see no reason why it wouldn't hold. But yeah, I think that analysis would be a cool thing to look at for sure.
Okay. Yeah, I think you did run quite a few ablations that the
yeah. Yeah, thanks to all the reviewers for that. Yeah.
Cool.
Yeah, there's still not enough apparently. But yeah, so just to kind of show this in practice, if we look at DQN without a target, a target network or a replay buffer. Sorry, this is testing in CartPole. Compared to PQN just with one agent, so we're not parallelizing, but essentially just using that LayerNorm Q function approximator. You can see the performance on the right is it's like stable, pretty relatively short number of time steps, but on the left you never get to a stable solution. So again, this was another kind of empirical sort of validation of that result. Cool. So so I'm conscious of time. Part 2, how do we kind of put this into practice? And this is when Matteo basically came in and really kind of took this to the next level with his introducing a kind of parallelised Q learning algorithm, which is it was really cool. So if we kind of look at the family of Q learning algorithms, we have the first one, which was like the online Q learning algorithm, where you just have a simple learning experience, samples from the environment. You then update your Q values. They then allow you to interact, and the process kind of continues. The implementation of this is super simple. It has very low computational memory cost. However, as we've seen, it's for nonlinear function approximation and off-policy sampling, it's unstable, so can't really be used for deep reinforcement learning settings. DQN was a major breakthrough. It essentially showed that, at least empirically, that you can kind of stabilize this thing by introducing a replay buffer and target networks that are kind of updated periodically. The implementation, the kind of difficulty of this is kind of medium. There are some hyperparameters associated with the size of the buffer, the target network kind of frequency update, but it's incredibly difficult. However, the computational memory cost for this is high. You've got to store this massive replay buffer of interactions. And the kind of delayed updating in the target parameters slows down the kind of updates of your algorithm. It is stable, like as I said in our previous paper, we kind of it's kind of stable, with a caveat. Basically, it kind of relies on fitted Q iteration being stable. So if you can show that fitted Q iteration is stable, then you can show for non-diminishing step sizes that DQN and target networks can also stabilize the update. Whether fitted Q iteration or not is stable in every setting, I'm not sure. I don't know if anyone's shown that, but empirically that kind of seems to hold. And then you can kind of take this one step further, and you can have multiple copies of your Q network with actors essentially acting asynchronously in parallel. And you can have like a replay buffer of all of their interactions and use this to kind of update your Q network. The implementation of this is tricky because you have to kind of manage all of these separate interactions and all of these kind of copies of the Q networks. The computational memory cost is very high, in particular the memory cost, because the replay buffer doesn't just contain like samples from a single agent, it's samples from all sorts of agents across the network. But it is kind of stable. And what Matteo wanted to do is kind of combine the best of all of these into one algorithm. So to do that, he came up with kind of the PQN algorithm, and this is kind of essentially the same as like the simple Q-learning algorithm, obviously using the LayerNorm to stabilize it, so we can go back to the standard kind of Q-learning algorithm. But what we have is we have a kind of vectorized environment, so in basically like an environment coded in JAX that allows for like parallel kind of interactions to happen at once. And we have a single Q network with a parallelized agent taking multiple actions at the same time. That then gives us a learning batch. Then that's then used to update the Q network without having to store it in a replay buffer because of the stability properties sort of identified earlier. So it's basically just vanilla Q learning with a regularized Q function approximator and I separate interactions in parallel with a vectorized environment. So we see that the implementation is very simple. It's not really too much more difficult than like just the standard kind of Watkins Q learning algorithm. The memory and computational cost is low. We kind of throughout all of our experiments kind of compared to the best baseline, you can see that we've saved, you know, like up to hundreds of gigabytes of memory and kind of sped these things up to kind of 50 times. So in Atari in particular, we compare to like DQN. Obviously we get all of the nice kind of stability guarantees from the theory. So the theory has essentially, you know, allowed for the best of all approaches, and this is kind of why I advocate for papers that combine kind of theory with empirical contributions as well. I think there's a real sort of power where you get that kind of synergy, where what one essentially influences the other, rather than kind of people going off and like shooting in the dark, getting an empirical result, and then kind of theory catching up with it. Yeah. So what are the additional benefits? Well, we can, you know, as I mentioned earlier, yeah, we actually extended it to PQN lambda. So that's a simple parallelized extension of the lambda returns algorithm by Daly. It's a kind of truly asynchronous approach. So in a lot of previous asynchronous methods, updates still depended on historic policies. And this is kind of good because essentially you're not relying on historic distributions in your updates. So for PQN, it's kind of because you're sort of sampling in parallel, it's always using the kind of policy at the current time step. And with this as well, it means that RNNs can kind of simply be integrated into the setting without the need to kind of propagate gradients from historic sort of states in the replay buffer. So this makes like the integration of recurrent neural networks really easy. And we kind of look in like the multi-agent setting and settings like Craftax, we use like PQN with RNNs in our results. Cool. So just to kind of summarize the Atari results, we compared PQN to Rainbow, to PPO. These are all kind of Matteo's results. He knows a lot more about the details of this, but yeah, and you can see that you know, using like a fraction of the computational time, we can achieve like pretty near state-of-the-art performance using our kind of PQN algorithm across the Atari benchmarks. Yeah, full details are in the paper on this. I think if you have any sort of questions on the exact implementations, we've got a GitHub with code, and also Matteo is definitely the best person to ask for this. We also tested in the kind of Craftax and multi-agent environments. So in Smax, Overcooked, and Hanabi, and yeah, we kind of recover, you know, that PQN is a it seems to be a kind of like very simple but very effective algorithm that's kind of competitive with a lot of approaches. Cool. Yeah, thanks for watching. I think the one, yeah, if you want to try it on our GitHub, as I said, like the links there through the QR code. The one thing I think with PQN that I think the most important thing to like extend on it, and something that I'm trying to find time for, but would be a kind of cool collaboration, would be to look at exploration, because at the moment exploration, we're only just using like a simple epsilon greedy type approach, but what seems to be holding us back from beating kind of benchmarks with better exploration is essentially that. Like, and I think the parallelised sort of nature of PQN sort of would lend itself really well to some kind of like ensembling or Bayesian exploration. So if anyone, you know, wanted to kind of collaborate on something like that, I think that would be quite an exciting next step. Cool. Yeah. Thanks for watching.
Cool. Thanks so much, Mattie. I think
No worries.
it was a awesome presentation, and just like I really enjoyed you also just going through like TD learning and sort of the challenges there, and not just going to the contribution. So thanks so much. I think a lot of people sent clap emojis in case you didn't see.
That's great. No, I can't see.
You can't see. So
yeah.
what I'm going to do is I think I will stop the recording, but still stay online for people if they want to ask more questions. But I'll stop the recording. Thanks again. It's really
no worries. Yeah, no, thanks for having me. It's been good. Thank you.